et al. And a lot of fellows from DeepMind, including Botvinnik. Okay. So the key takeaways from this paper, in my opinion, were basically they came up with an idea of convention, which is even though people in a society have very different preferences from each other, they can coordinate amongst themselves for a collective good of the society, which may not be perfectly in line with their previous preferences or tastes. And such conventions, mostly when we think about it, it's mostly something like a treaty, like an international treaty or something. And those things seem to us as very calculated, rational stuff, which mostly comes from the model based perspective of humans. And model free perspective of humans is mostly, habitual learning and stuff like that. So these people try to form conventions from a model free perspective. And in this thing, they use like a temporospatially extended game. There are multiple agents, each have a different reward mapping, and it's incomplete and imperfect information, which I will explain what it is later on. And they come up with two different problems, which they empirically show like this is a problem in this setting. It's called the startup problem and the free rider problem, which again we'll come to later. So these are the key takeaways. Now, um, where do we exactly, this is basically whatever I said before. So what exactly do we, where exactly do we find model free convention in real life? So the paper gives the example of, let's say, a new member in a band. Um, so they rehearse till they achieve coordination, but mostly rehearsal is something which is habitual, as in playing the instrument. So that's kind of like a model free convention. And similarly, we could basically, if I just pick two people, we could row a boat together, even if we can't communicate at all. And this is model free because these are insensitive to rapid fluctuations, as in, if the conditions change, then we will have to do some amount of trial and error to get to a new equilibrium point, which is like, but then after that, we could obviously row the boat again because, yeah, we can do that. So the model they come up with, and there is a lot of mathematics here, which I copy pasted from the paper, but I'll try to condense that. So as I said, it's imperfect and incomplete information. Imperfect being that each player in the multi-agent setting has some amount of information which is not known to other people. Some common examples might be cards in a poker setting and something like that. And incomplete information is the rules of the game are not known. So we need to play them and discover the rules. Formally, this is like there's an observation function which is maps from the entire state to like a d-dimensional view of what a single agent can see. And in each state, I'm allowed to take an action from the set A of I for the ith agent. There's a transition function which maps the state plus the entire action to like a different state. And there's a reward function which is a function of the state and all the actions taken by the different agents. Now, the heterogeneous preference in this case is something like the game has k different berry colors, and an agent obviously will prefer to consume any berry over consuming no berries. But then each agent has a berries. Whereas conditional preference is basically I have to assume that the other people in the world are acting in a certain way, and I will take my action based on how they are acting. So how would we define a convention in this? The convention, these people define it as like a divergence from the unconditional preference, a divergence of the conditional preference from the unconditional preference. So again, this bit of mathematics is kind of like there's a function I, which indicates whether a berry has been eaten or not. And that is basically the state and the action which maps to 0 or 1, 0 being the berry has not been eaten, 1 being the berry has been eaten. And then there's a certain set of functions, G, which is like a reward mapping from the indication function to a reward which will be obtained by the agent. And since there'll be like different reward mappings, that will correspond to agents having different preferences of berries to eat. And there's a function mu, which is like the distribution of states. So we could probably think that the expected value of equilibrium would be like the reward mapping into the expected distribution of states summed over all states and actions. And as usual in RL, there's this, the agent wants to maximize its own discounted sum of rewards, which is denoted as the value function from the initial state S naught. Uh, okay, I'll get to this a bit later, the agent architecture details, because I want to cover how they exactly define convention. So it's kind of like the dissimilarity between the produced behavior versus the expected behavior, let's say, uh, in an unconditional setting, which is basically like a completely uncoordinated state. So they say like let sigma be a empirical signature function. And they define how to select that later, but let's just assume that it is an empirical signature function, and mu being the distribution over states for a joint policy pi, starting from S naught. So let's say the expected empirical signature would be given by sigma this. And if the agent does follow a pi taste seeking, which is completely unconditional, then we'll have an expected signature, which is sigma ts. So now we can define the degree of conventionality as a function m of sigma ts and sigma, where m can be any measure to compare two distributions, so let's say the KL divergence or something like that. And how would we come up with the signature functions now? So they postulated that to get a valid signature function, it needs to satisfy two conditions. It needs to be causally downstream from agent actions, meaning that as the agent takes actions, the signature must change, and it should be insensitive to additional agents who are selecting a free riding strategy. So for this, I'll have to tell you what a free riding strategy is. It's basically, let's say even though going to a state of common good is preferable for everyone, as a single agent, I would prefer to spend my time being taste seeking, completely greedy, whereas I would prefer other people to follow a policy which is doing good, kind of like a very greedy sense. A valid signature function which they use is like a k-dimensional vector, which is b1s, b2s, and up to bks, where bks is basically the fraction of k-type berries present in the entire game. So the architecture details. Oh, okay. I think I'll get to that after the game. So this is how a game state looks like. Here's a player. We have all these different types of berries here. Now, the game initially starts with unripe berries, and the unripe berries can translate to a ripe berry through a function which I will come to later. Like there's a probability of an unripe berry transforming to a ripe berry, and the players are allowed only to eat ripe berries. Now, some other things they can do is they can plant their own type of unripe berry if they want, and then that has a probability of turning into a ripe berry later. They can also use a zapping beam, which is like it will, for some amount of time, temporarily freeze every other agent. And so I could maybe use this temporary time to feed on whatever I want to, or plant my color of berries if I want to. And the so the probability that the berries ripen is a function of the fraction of the total number of berries present. As in, the probability that the berry will ripen to a red berry is like a function of the fraction of the red berries present amongst the total number of berries. And they say that f is a completely monotonically increasing sharp function. So there, so let's say there's like only, so let's say we approach a monoculture in which there's like only one type of berry present. In that case, f of this thing will reach an optimal point, and that should be the that is a very advantageous position if the agents can come to a convention saying that we just plant one type of berries and uh, diverge from what my taste seeking signature tells me. Now I could come to the agent architectures. So it's like there's a sprite, which is basically like a section of 8x8 from the state. And an agent would receive 11x11 stripes as an observation. Now there's a network which will produce a policy pi I and an estimate of the value function, which I forgot to turn it into an equation, but okay. And this is trained using importance weighted policy updates sampled from a queue of trajectories, as was done in the Impala architecture by Espen Holt et al. And this the network was a pretty basic network. It's like two convolutional layers, two fully connected layers, then an LSTM to basically keep the memory in place, and it's finally mapped to a policy and a value function. So it's not much new there. Um, so now we come to what combinations they tried out. They tried out four settings. One is like initially everything is of the same color. Everything is unripe, but it's of the same color, and there's just one group. So they all have just one preference. Then there's like everything is of the same color, but then there are multiple groups. Then there's initially there are like multiple colors of unripe berries, but there's only one group, so there's only one taste. And the fourth one is it's all mixed up. There's like multiple initial conditions and multiple groups with each different preference. And they do quantify the conflicts here, as in the first one, there'll be no conflict because obviously everybody's taste is the same, and that's the only type of berry present, so they'll just keep eating that, which is obviously advantageous to them. In the second one, there's a problem of unequal outcomes in which people, in which the in which the groups of agents have a difficulty obtaining, like communicating with themselves and coming to a convention. But they sometimes do come to a convention, which is what they state later, and I will cover it. And then in the initial pentaculture, which a pentaculture in one group, there's like a free rider problem, and pentaculture even groups, there's free rider and startup problem. So according, so covering the monoculture states, it's basically saying that the fraction of berries is one. Basically, all the berries are of one type. In the paper, they show that this is an optimal state since f of ms is optimal, hence the berry conservation is maximized. So how is this done? It's kind of like the berries are being made instantaneously, and so I can just keep consuming the berries, and be they'll keep being made instantaneously. And so it's like I'll just maximize the consumption of berries in that state. Now, there are k different monocultures because there are k different berries, and each monoculture is kind of advantageous to a different group. But if I shift out of a monoculture, it will be disadvantageous to all. And the obvious problems coming here are the startup and the free rider problem. So the free rider problem is basically something like, let's define a monoculture fraction called M, which is basically the number of dominant berries divided by the total number of berries. And the expected monoculture will be defined as this, where mu pi is the distribution over states. Now, empirically, they observe that after a certain M bar, which is the expected monoculture fraction, the individual agents, they are kind of adamant to follow the policy that leads to the common good. So because the reason can be stated as since I am spending my time for trying to follow a common good, there's a certain opportunity cost which I could have utilized by planting a berry which is of my taste. So even though everyone will benefit from the emerging monoculture, every agent wants to spend their own time planting their own berry, and they want to rely on others to put in the effort to increase the monoculture fraction. And this is why it ends up at like an incomplete monoculture, but still that is an equilibrium. And the startup problem. So the startup problem is that when there are different mapping functions, as in different tastes, there's a certain disagreement between individuals as to which monoculture to prefer. And this is mostly present in setting 4 and 2, which has like more than one groups. And it's more prominent in this setting than in the initial monoculture setting. The problem here is basically there's a certain disagreement. So sometimes it is possible that you can achieve like a final state in which all the berries are like there's a dominant culture of berries, but mostly there's a low reward and they just keep fighting amongst themselves and they don't go anywhere. Some way these people thought of mitigating this problem is increase the number of individuals in one group. But again, they note that it's necessary but not sufficient that it'll sorry it's sufficient but it's not necessary that they will achieve a high reward state. Um, so if you take evenly sized teams, this is the Berry distribution, which there's a certain disagreement. So there's not a maximum of any single state. Whereas this is what should happen. If they say that this is a maximal state, which is a maximal state, then it should be something like everything should come down and one should go up. Um, Now, as they vary the proportion of players, these are the states which come up. These are still incomplete monoculture states because of the free rider problem. But then these are very few as compared to all this. And yeah, so basically there are only some runs which achieve this higher reward state. And this shows like the equilibrium, not the equilibrium, the function of, the most common color versus the number of berries eaten. And it's obvious that if it achieves like one color, then the number of berries eaten will be more. So now these people, they try to study convention formation in the long term. So they start by stating that there are 2k plus 1 stable states. There's a base conflict state where the fraction of all the berries is equal. And there are k incomplete monoculture states, which they do basically the incomplete monoculture state is I overcome the startup problem, but then there's a free rider problem, and so I can't go beyond that. And then it's a perfect monoculture state. Now these are some of the long-term results. So this is like the Berry distribution over time. Okay, so this is how they distribute the players. There's 11 in red and 5 in green, 4 in yellow, and 4 in the remaining color. Now, as you can see here, after a point, the red reaches a maxima, and everybody's favoring the red. So till a point, the red is kept as the primary support, but still there's kind of some support for green and yellow. These are the secondary supports. But after a point, the yellow people give up their yellow support to support the red berries, and that reaches a maximum. Some other things which I saw is the replanting rate. So in the red group, obviously, everything will start with certain high replanting, which basically says that at the start, everybody wanted to prefer their own color. So that's why it's high. But later on, as these decrease and some obviously come to zero, the red rate is pretty high. Coming to the green was always like a secondary support. So the green is also high as compared to all the others. But interesting happens when we come to the blue and the yellow part. So initially the blue was high because they wanted to support their own culture, but then they come to a convention in which they start supporting the other colors. Most notable of these is the green and the red and the yellow as well. So there's like green is the secondary support, yellow is the secondary support. But after a while, they give up the secondary supports and focus on the primary. And even though the rate of planting is coming down, red is still the highest. Similar for yellow. As you can see here, like after a point, yellow gives up its own support to go and support the red. And it's evident from here, it says that yellow is pretty high at the start, but then it goes down and they support the red, and green, which is kept as a secondary support, increasing, which is like the agents are kind of coming and coordinating with themselves, and so they don't have to do much of replanting. There's not a lot of competition there. Everybody wants to just plant red berries, green berries as well, but mostly red berries. And they also noted that zapping, which was like I can freeze the state right now so that only I can take actions and nobody else can take actions. That reduces as time progresses and as the fraction of red berries increases. So yeah, that's it. There's a lot of parallels which these people show in a multi-agent setting from the real world, as in maybe I have a very biased opinion of the real world, but that's how I think of it. There is obviously a startup problem in which, even though I'm doing something for the common, even though not me, that like some people who are doing something for the common good, it's not always that their movement will take off because maybe their numbers are too less, and there's always this fear in their mind that whatever they're doing for the common good might be in vain. So why not just focus on, maximizing my own taste? And the free rider problem, obviously, which is like I leave other people to do the common good thing. I'll just focus on myself. But then, yeah, there are certain conventions which do come up, and sometimes conventions can be helpful not just for me, but for like the entire. Okay, the whole point of convention is that it's supposed to be good for the entire population. But then sometimes me following a convention, uh, keeping in mind that others are following the convention, can be more advantageous to me than, let's say, me just doing what I want to maximize my own taste versus, let's say, others are trying to follow a convention as well. So yeah, those are the two points I thought was relevant from this paper. And something which I was still curious about is how do we come up with like an experimental design to get rid of the startup or the free rider problem? Because as they said, increasing the population of one might get rid of the startup problem because, well, there are a lot of people trying to maximize, let's say, the red objective. So um, it's not like their efforts will go in vain, but still, it's not always that they reach a proper monoculture. And secondly, the free rider problem, I don't know, maybe you could change the reward function somehow, but I'm still curious. I have no idea how this will be done. And yeah, that's it. Like a pretty short paper and a pretty short session. So, any questions? Oh, there are questions in the chat, is it? So, there are no questions by anyone. Am I audible?
Yeah, you're audible. So I wasn't there for the whole time, but and I'm not sure if they cover this, but are there cases when the conventions themselves change, like the optimal convention for everyone, if that changes, and so they they kind of adapt to that?
So there are cases in which, so let's say there are k different monocultures, right? So there are cases in which there's shifting from one monoculture to the other. But as they do say in the paper, that being in a monoculture, like being in a red monoculture, is obviously advantageous to the red group. But then shifting to a different monoculture, it will just be advantageous to like a different group. But in the end, shifting from a monoculture to like a non-monocultural setting would be disadvantageous for all. So there is this shuffling between equilibrium states. But
Mm-hmm.
in the end, if they do reach a monoculture, they prefer to stay in a monoculture. Does that answer your question?
Yeah, right.
Okay. Anyone else? Okay, maybe someone could try to answer how we could change the experimental design to um, get rid of the startup or the free rider problems. Any ideas there? Okay, fine then. I guess this is it for today, unless anybody has anything else to say.
Yeah, I guess so. Any questions, anyone?
Because this is spooky now. It's so quiet.
Yeah.